over to you, TJ. So calibration issues in epidemiological modelling.
Brilliant. Thanks, Kira. And thanks to Peter and Jane and the organisers for allowing me to come and talk. So I'm going to present. So this work is very much ongoing work, and it's ongoing work trying to think about how we can use UQ methods to calibrate a large-scale stochastic metapopulation model of COVID-19. In the spirit of the title, I'm very much going to be presenting the challenges that we've come across, and unfortunately not many solutions yet, but potentially some way forward. So to give a bit of background, so one of our collaborators, Leon Danon, the University of Bristol, a few years ago, developed a framework for implementing sort of stochastic compartmental epidemic models on top of a metapopulation structure. So in this case, effectively the country is split up into electoral wards, and epidemics are run within each ward, but based on travel commuting data, individuals can move between wards. Okay, so you know, you might have a sort of more systematic work movements or commuting movements, and then other movements due to, you know, leisure time movements and so on and so forth. So the idea is that you effectively can generate a spatial spread through this network of commuting data. And at the beginning of the outbreak, Leon got some money, and together with Christopher Woods at Bristol, they turned this into a general purpose Python package that enables people to write sort of customized epidemic models and embed them within this sort of metapopulation commuting structure. And if anyone is interested, there's the software is all available with documentation at this website down here. And Leon came to us and sort of said, well, look, you know, it would be really interesting to see whether or not it would be possible to calibrate a model built, you know, using this software, because, you know, there are certain sort of policy questions that could be explored by having models that are defined at sort of higher spatial resolution. So that was the kind of original sort of challenge that we were sort of set with. So we developed a model in MetaWards, and our current model looks a bit like this. So individuals begin susceptible, sometimes they become infected. If they become infected, then some individuals will become asymptomatic and eventually recover. Some individuals will become symptomatic and they will get sick. Some of those individuals will recover, some will die, and some will go into hospital, of which some of those individuals will eventually recover and some will pass away. So this is a sort of fairly standard model structure for COVID. We have parameters in the model that govern not only the transmission terms, but they also govern the amount of time, the length of time that individuals spend in these various compartments. And importantly, what we wanted to build in from the outset was some age dependence, particularly in terms of the probability of transitioning down these different pathways. So it became fairly clear early on in COVID that there was a, you know, the chance of you having a more severe outcome is very age dependent. And so some of these parameters, particularly the ones governing the transition probabilities, we have built age dependence into this from the outset. If anyone is interested, all of the model and the model development and the various things that we've tried are all published online on this website, and we were sort of hoping to just keep putting stuff up as and when we do things. Because we have age structure in the model, we have age categories, we also have age dependent transmission. So we use data from contact survey data, so from things like the Polymod study and more recently the COMIC studies that look at, so these are data sources that give us some sort of estimate of the contact rates between individuals in different age classes with other age classes. And so we can build this into the transmission potential. And this thing on the right hand side, don't worry about the actual numbers here. This is really just a simulation of the model, just really to show the spatial kind of structure of the model. So this is effectively what we're sort of working with. And we're trying to calibrate this in the first instance to things like deaths and potentially hospitalizations as well. So from a calibration perspective, if we observed the right things, so specifically in this model, if we observed the number of individuals in each of these states at each time point, at each region of space, then conceptually we can actually just write down a likelihood function for this, and we could solve this in using whatever Bayesian or maximum likelihood type method we wanted to. Okay, and the likelihood function takes this sort of form where, so I'm using pi here to just denote a generic sort of density function, but essentially we have so x here corresponds to the hidden state, so i.e. the numbers of individuals in each of these classes, and I'm going to use z to correspond to the data. Okay, so what our stochastic model does is it propagates individuals through time. So propagates the states of the system at time t-1 to the new states at time t. Okay, so this is our stochastic model. And then conditional on the hidden states, we have some stochastic observation process, which maps our hidden states to our data. Okay, and we have a time series, so we sort of product this across the time series. And of course, the challenge from a statistical perspective is the fact that the x's are all unobserved. And so essentially to get this likelihood, we would have to integrate over all of the possible unknowns, right? So all possible epidemic trajectories that we could think of. And obviously this is a very high dimensional integral, and it's not one that we can calculate analytically. So there's been lots of methodological development looking at ways of estimating this integral, and we can do it. But typically we can do it in much smaller populations. They effectively, the methods are incredibly computationally intensive. And so when you start to try and scale this up to a model that is as complex as the MetaWards model that we're working with, it just becomes infeasible. So we were trying to think about ways in which we could do this, but by leveraging some of the UQ technologies, particularly emulation, things like that. But we ran into some challenges that hadn't come up in other models that we've been using. So I'm going to sort of run through a few of these just to give you some ideas. So the first is that stochastic infectious disease models can induce behavior which is somewhat difficult to emulate. And I'll give you a couple of examples of this, but these are sort of behaviors which don't manifest in deterministic models. Things like multimodality, for example, in outputs. What we've discovered, particularly with the spatial model, is that seeding becomes really important. So not only how many introductions of infection you have, but also when and where those introductions are made. And in the early stages of the disease, the model trajectories through space can become very sensitive to these choices. And we really, for COVID, don't have a very good idea of where infection came in and when. And we are interested here in calibrating to spatial regions simultaneously. So in actual fact, we do not calibrate to wards. We aggregate up our model to local area district level. And there are about 300 of those in the country. So we're not sort of aggregating things up to the national level. We want to be able to emulate or to model the model fit within these spatial regions simultaneously, which means we either have to build lots of emulators or we have to come up with some way to do this in a sort of maybe by data reduction or something like that. The other thing is just that it's actually taken us a very long time to run the model, because we are developing both the MetaWards model itself, and MetaWards itself is developing, as well as the UQ. And these models take a long time, and most of the time is spent waiting for them to queue on HPCs before we can run them. So it's just quite a slow process that we've come across trying to do this. So to give you an example of what I was discussing with the seeding, here is some data. So we've run the model now up to the first lockdown, and what I've plotted here is on the y-axis are the proportion of deaths in the country at the time of the first lockdown, and on the x-axis here are the different regions, so northeast, northwest, and so on. And the black dots correspond to the data. The grey dots here corresponds to a run from an ensemble of design points across our input space, and the green dots correspond to ensemble members that give us roughly the right number of deaths when we aggregate up at the country level. Okay, so the model is perfectly capable of producing the numbers of deaths which are consistent with the national totals. But what you can see here is that none of these ensemble members get the spatial distribution right. So we are always underestimating the outbreak in London, and we are always overestimating the outbreak in the East. And the key question is, is this because the model or the parameters are wrong in some kind of way? Or is it because we are just putting the seeds in either the wrong place or at the wrong time or at the wrong levels? Okay. Now, again, in a perfect world with infinite computing resources, then we could potentially put a prior distribution on import rates in each region and allow the model to calibrate. So end up with a posterior distribution for introduction to infection within each local area district. But we just can't do that here because there are too many of them. And so we've been really struggling with how to deal with this. Now, this sort of behavior, so another type of behavior that we get, I'll come back to the seeds in a second, but another type of behavior that we get with stochastic models tends to happen specifically when we start off with low numbers of infections. So here is an example. So this is a plot from a paper that we published a few years ago now. And this is, what I've plotted here is a posterior predictive distribution for a model of Ebola. So a single population model. And what I've plotted is the final removal time. So effectively, we take our posterior distribution, we take samples, we run an epidemic, and this plots the time at which the epidemic died out. Okay. And what you can see here is that there is a very high probability in this case that an epidemic is seeded but dies out pretty quickly, so within 50 days or so. But also, if it sort of gets beyond 50 days, then it tends to run for a long time, right, and infects lots of people. And in fact, although you might think that this is a function of the ensemble, in fact, it's not. This is a function of the model. And in fact, if you take the posterior mean estimates, for example, and you just fix those, you get the same pattern. Okay, so this is something which comes up in stochastic models that does not come up if you fit a deterministic model, right? In a deterministic model, you'd end up with a prediction that would be around 200 days, okay? Now, the data here correspond to an epidemic that ran for just over 200 days, okay? But you can imagine that if we simulate from this model, and we just simulate forwards and we don't do anything else, if we have finite computing resources, then there's quite a high probability that we just end up simulating things that look nothing like the data. Because there isn't this nice smooth distribution. Now, if I look now at the trajectories, and what I've done here is taken all of the epidemics that last beyond 100 something days, okay, and I plot those out so that the white line here is the data and the black bars correspond to the posterior predictive mode. You can definitely see that we can get trajectories that do look like the data. But if we average across the whole ensemble here, then it pulls this mode down. And you can also see that the variance, so this is the posterior predictive distribution here, you can see that the variance is also changing along the time course of the epidemic. So stochastic models can induce quite wide variability in trajectories. And these challenges are exacerbated in certain regions of the parameter space, but in particular when the number of infectors are low, right? So at the beginning of an outbreak, for example. And if you think about what we're doing with our spatial metapopulation model, what we're doing is taking a massive population and splitting it into lots of small regions and introducing a few seeds in each region. And that means that the potential range of spatial trajectories that we could get in the early stages of the outbreak is huge. Okay? And what we have observed in the data are potentially one realization from that process. Okay. And so what we the two things that we've been thinking about is firstly that we probably need some kind of data assimilation mechanism just to try and put more weight onto trajectories that are more like the data. And also perhaps some mechanism for trying to deal with the seeding. And maybe we're just putting seeds in the wrong place. So with regards to the data assimilation mechanism, the approach that we're going with is a sort of particle filter type idea. Just to illustrate essentially how this works, so this is sort of one-dimensional example. Imagine that we've got some state on the x-axis here and y-axis, sorry, and time along the x-axis. What we might do is start off with a bunch of samples from our initial condition distribution, some sense. We simulate forwards based on our model. And then we have some data, which is the red dot here. And remember, we have this observation process around our data. And so we use the observation process effectively to weight these particles so that particles that are more consistent with the data have a higher weight. Now, in the bootstrap particle filter, what we then do is we resample a new set of particles from these particles proportional to their weights, and then we simulate them forwards. Okay, so particles with low weight often don't get propagated, and particles with high weight might get propagated more times. Okay, and then we repeat this process again, and so on. And you can see that what happens is that trajectories that begin to deviate far from the data tend to be removed in favor of trajectories that are closer to the data. And this is the basic idea of data assimilation. Now, when you first think about this process, and it worried me for a while because I couldn't quite get my head around this, but it feels like you might be introducing bias in some sense into the system by doing this, because effectively you're sort of selecting trajectories that are good. But from a likelihood perspective, that's not true. So you can generate an unbiased estimate of this likelihood function from the particle weights. And furthermore, it turns out that that estimate of the likelihood is both unbiased, but also has a much lower variance than you would get if you just did a sort of naive Monte Carlo estimate. And so this data assimilation can be really useful because it can nudge things towards, so you use information from the data effectively to feed into your simulations. And that could help us to control this spatial spread in some kind of sense. Now, again, there's lots of ways that we can work with this. Our current idea that we're working on is to think about whether we can emulate this, this likelihood estimate, which would have various advantages. We wouldn't have to reduce the data, we can incorporate data assimilation, and we only have to emulate one thing, as opposed to, you know, emulating lots and lots of regions separately. The flip side is that it might be quite a hard thing to emulate. So at the moment, we are trying to use deep Gaussian processes to do this. There is a sort of precedent for doing history matching and things on this surface, and there's a nice paper by Jeremy Oakley and Ben Youngman, which involves some of these ideas. So this is kind of what we're working on at the moment. I don't have any results to show you yet, unfortunately. Oh, and I should say that data assimilation doesn't solve all of our problems, by the way, but it might help some of them. Now, another thing that we're trying to build in is a model discrepancy process. So sort of classic epidemiological model wouldn't have any model discrepancy. So we would simulate forwards from our model and then weight according to the observation process, carry this through. But we know that our model is deficient in various ways, which Danny discussed a little bit on Tuesday. So what we're going to do, the way that we're going to try and deal with the model discrepancy is by introducing another set of states here, which I'm going to call Y. And Y basically correspond to an adjusted version of X. So we simulate from our model and we get some hidden states, and then we run those hidden states through a model discrepancy term, and we get adjusted states Y, and then our observation process is conditional on Y. And then the crucial thing is that we then pass the adjusted states through as inputs back into our model, and we continue this through. Now, the distribution that we've chosen is a truncated Skellum distribution. So effectively, this is a discrete distribution, and we can set it up so that it has a zero mean, but we can set the parameters, and that allows us to control the variance. So we can control sort of how much discrepancy we add, and we could also potentially make these parameters a function of the data, so we can allow for variable amounts of model discrepancy at different time points or as the states grow, and various different things. And we're hoping that this in and of itself might help us to adjust for some of these, particularly things like the seeding.
TJ, sorry to butt in,
yeah.
but you've got about 2 minutes left.
Yeah, no problem. Cool. Thanks, Kira. So the only thing that I should say about this is that because we are adjusting the actual states, we do have to be a bit careful with adding noise. So we have to make sure that the states are consistent. So for example, if we add more deaths through the model discrepancy, we also have to make sure that there are enough infections to allow those deaths. So in practice, the way we're working at the moment has a sort of truncated process on top of this. So this is kind of one of the ideas that we're working with. Again, it's work in progress, and we're still trying to figure out the details. The other thing we tried with regards to the seeding was this idea that what we could do is we could take an ensemble member and we take the first few weeks of data and we basically fit a simplified version of our model. So we turn all the spatial structure off and we assume that an epidemic, we have a prior distribution for the import rate in each region. And then we fit a model and to the first few weeks up to some time point t star. And we end up with an estimate of a distribution for the likely states of the system at time t star, okay, from this simplified model. And then we use this distribution as an initial condition distribution, which we plug into MetaWards at time t star, and we carry this forward. And we use an MCMC algorithm based on an independent individual forwards filter backwards sampling algorithm to do this. I'm going to skip over this because I'm running out of time, but essentially the idea is that it gives you distributions that depend on both the parameters and the different spatial regions. It has a few problems because obviously we're turning off the spatial structure and the spatial structure could be important. But this is the sort of thing that we've been trying to think about in terms of trying to work out whether we can learn where we should seed and how much we should seed and when we should seed in each of these regions. So just to finish off, MetaWards is quite powerful because you can allow, you would be able to develop your model in real time, which is good, and you could implement this on top of this meta population structure. But when we're coming to calibrate it, we still have running into these challenges, which again are just ones of particularly of scale and space that we are trying currently to figure out. So all of this work is ongoing. If you're interested in any of the stuff I've been talking about, it's all up on this website and we'll update this over time. Thanks very much to funding, by the way, Juniper and MRC, EPSRC, and to Jasmine and the University of Bristol as well for their HPC services. Thank you.
Thank you very much, TJ. That was very interesting. So do we have any questions from the floor? Or, Jake?
Thank you for that description. Just thinking of the idea of comparing models against a benchmark. What do you gain by a model that is intensely difficult to compute and takes a long time over perhaps a simple model that could be computed daily and updated, in terms of what criteria would you use to distinguish them?
So yeah, that's a really good question. I mean, there's definitely this concept of models being fit for purpose, right? And for certain questions, you may not require a complex model like this, but for other questions, you might do. So one of the key things is that the dynamics. So when we think about these sort of mechanistic models of epidemic spread, we know that the dynamics can change as you add things like network structure into the model. So so if you have a simpler model that doesn't build in the spatial structure, you might get quite different dynamics for the same parameter values, right? So R0 and things like that are functions of the model. And so the same R0 estimate that you get from a model without spatial structure might differ from an R0 that you get from a model with spatial structure. And so there are differences in the dynamics that one might get if you fit these models at different scales. But if you wanted also to estimate things like the impact of local lockdowns, for example, then that might be something for which a spatially structured model might be more informative than a model that doesn't have the ability to look at localized lockdowns, if you like. So it's a really good question, which is why you need so many different models. And really what we were trying to work with was to say, if you wanted to develop a model like this, could you actually fit it in a reasonable, robust manner?
We've got one more question and then we'll move on to the next speaker.
Richard Hibbs, British Isles DBT training. Thank you very much. Fascinating presentation. I'm intrigued by that early slide where you showed that the data from London was very much an outlier in comparison with the model predictions, but more which I can imagine reasons why that might be the case, but I can't quite figure out why the East of England regions, why the model was over predicting those. I mean, so the two questions are, do you think that's just a coincidence that it happened to be the East Midlands and the East of England? And if it's not a coincidence, what is your theory about that?
Yeah, no, that's a really good question. My theory about that is that so in these early tests, what we were trying to do was to have some sort of informative way of putting the seeds somewhere where we think they should be. And so what we did was we looked at the first few weeks of data and we saw where the deaths were. And we tried to introduce some seeds into regions where we knew that there were deaths, for example. And we tried not to be too prescriptive about this, because obviously we're aware that you know, maybe there's a big outbreak in London, in some areas, but you don't have the same age demographic, so it doesn't necessarily feed through to deaths in the same kind of way. But we tried to find a reasonable place to put them. And I think what might have been happening is that we just saw, because again, particularly at the beginning of the outbreak, there were problems with reporting, right? So you know, it could be that you know, deaths were not being reported, perhaps. You know, and again, in the early stages where there were very few of the deaths in the beginning of this outbreak, the infrastructure was not up in the same way that it is now in terms of recording and, you know, what you classify as a death or what you don't. So there's all sorts of kind of things that could feed into that. And I think what was happening was basically that we were putting too many deaths, too many seeds into regions, because we were trying to seed kind of roughly proportionately to the number of deaths that we saw. And I think that was not quite the right thing to do. So there is a question about whether our model is not capable of recreating the spatial spread. I think it will be. I think we're just putting the seeds in the wrong place. But this is the thing that we have been struggling with for months now, in terms of trying to work out how you do this in a systematic way. You know, because if this were to happen again and we did want to develop these methods and apply them in real time, then we would have to deal with these sorts of questions again. So this is what we've sort of been spending time trying to look at. But I think it's probably just that we're putting seeds in the wrong place. Because we don't have things like importation or air flights or any of that sort of stuff in our model, right? Which is one of the key problems.
Thank you, TJ, again for a great talk.
Thank you.
So our final speaker in this session is joining us again remotely. So is Walter Edeling from